Well, ladies and gentlemen, my name is Muniru Nyei. Wherever you are, good evening, good afternoon, good morning. I'm giving my presentation from Germany right now in my office. So the topic of my thesis topic was BIM in structural engineering, a study of interoperability between BIM platform and FEM software on structural modeling, analysis, and design. This project was coordinated with 3 companies. The first company it was not very official, it was just mutual understanding, was Sophistic. Sophistic is one of the leading German software developing companies that specialize in software design, in structural engineering, and now they are moving towards BIM. My thesis has been coordinated by, I work with Sophistic. Can you see where I have Sophistic and Polytechnica?
Yeah.
Okay, I work with Sophistic. As I mentioned earlier, Sophistic is a German software developer for structural engineering, and now they are doing a lot of innovation in the interface between Revit and Sophistic. And then Polytechnica is an Italian engineering company, comprehensive, that provided me the data to prepare my thesis. The content is, I have an introduction, and I will explain a little bit about BIM and structural engineering, interoperability, a case studies, and a conclusion. My entire thesis is just summarized in this picture. The thesis statement, the objective, the scope, and the methodology is summarized right here. We try to look at the interoperability of BIM data in structural engineering, specifically focusing on direct link data exchange between BIM authoring tools and FEM software. In this picture, our aim was to identify what are the effective and efficient means of interoperability available for structural engineers. And then the second part was we try to look at when these data are exchanged from a BIM authoring tools like Autodesk and move to an FEM software like Sophistic, RFEM, CI Engineer, how does this software receive this data? Do they get all of the engineering data correctly? And the next aspect was trying to look at the entire structural engineering BIM workflow. And later on, we discuss some of the benefits and challenges. So some technical background, we identify that within the scope of structural engineering, there are 3 main BIM uses that were identified, even though there are other ones, but 3 main. Coordination, specifically interdisciplinary. For example, if you have an architect coordinating with the structural engineer or an MEP, that is widely used in the area of structural engineering. And then documentation. After you design after you go through the entire design workflow, you need to document it. Later on, we will show you how these documentations are done. And then for analysis purpose, like structural analysis and design, later on, we will discuss these BIM uses as well. Structural BIM model. A structural BIM model, it has, normally when you have within the BIM cycle, you have the structural BIM model, and within the structural BIM model, you will also have the non-structural BIM model, such as or elements that do not bear loads, but they must be included. But then within the structural BIM model, you have the physical structural model, and then you have the analytical model. The physical structural models focuses mainly on the load-bearing elements. And then the analytical model is the modified version that you use to perform all of your analysis. Later on, you will see this in what I'm talking about. And then in our thesis, we work on the workflow that is perceived to work within the structural domain that is popular. Most people that are using the structural engineering workflow cycles. Initially, you have the central BIM model, as I earlier on mentioned, where you have all of your data are populated. You have the history of the project, the name of the project, who owns the project, the families, and everything is populated here. And then once you have this as a structural engineer, because when you are creating this in Revit, Revit automatically generates the analytical model as you are going along. When there is no analytical model of a particular element, there is a possibility to transform it to enable analytical model in Revit. And if that doesn't happen, these things will not move to the FEM software. From the analytical model, and then you are able to create an FEM analysis where you perform your structural analysis and design. With Sophistic, how this is done, when you have the FEM analysis, then you move to design and detailing, and then documentation. So in our thesis, these are the workflow we identify and we follow. And then the benefits. Obviously, within the domain of structural engineering, productivity is very key here we're talking about, because these BIM workflow allow the engineers to share information as fast as possible, even though from the beginning it tends to be difficult because you have a deep learning curve. But once you are able to set your parameters right, when you have everything correct, these things work very fast. And then coordination and consistencies of data is another benefit. Visualization and simulation. When you are doing your structural design, when you are able to visualize and simulate, you clearly are able to see some of the inconsistencies in your model and your data, and you are able to see where there are clashes, and then the team is able to come back and say, okay, let's discuss it further and make modification. Analytical model purpose is one of the benefits as well. Documentations. And then there's one benefit, that the rise that I will refer to as the rise of downstream innovations and technology. As a result of BIM, there are a lot of downstream innovations. Like you see, Dynamo is coming, or we have Caranda, all these Rhino, and all of these things that are coming because of this, the BIM, the existence of BIM, of course. In the midst of these benefits, there are also some challenges, such as time and resources. To adapt BIM in structural engineering, it requires some time and it needs some resources. But that does not underweight the benefits. But these are just challenges. They are not difficulties, but they are challenges. And then the structural engineering is also a challenging field. You need to have specialist skill. Otherwise, the modeling process will be a futile effort. And then the model requires frequent updating and authoring. Interdisciplinary knowledge is required. Coordination, bottlenecks. Sometimes even in my office here, we have similar problems where we have to coordinate with the architect. There are always some problem. We have to change and come back. However, these do not outweigh the benefit. They are just some challenges. We look at interoperability. The definition as in ISO is the ability of two or more systems or components to exchange information and to use the information exchange. This is very important. It is not just about exchanging the information, but you must have the ability to use and reuse the information exchange. And this interoperability is what we are interested in, how this data moves, how we exchange data from one file to another without exchanging parallel files. We identify, for BIM to work in structural engineering, we identified 3 levels of interoperability. We have the direct native file exchange, the IFC or Open BIM format, and we have the direct link data exchange. As I indicated here in the green, my focus is on this direct link. That's why I put a green mark. This is an example of direct native file exchange. When Revit, you link an Autodesk model with that of Revit, because they are of the same company. This is native file exchange. That's one way you can exchange. When you exchange Microsoft Excel documents with with Word document, you are all talking about direct native file exchange. IFC, as you see in this model, this is something I did during the course period. I exchanged a Revit model with an IKEY card. That's one way. And then we have direct link or bi-directional or round-tripping engineering. This is where you centralize a model, you use Revit as a central database. Once you have this central database, and then you are able to exchange these informations to all of these software, and then you come back. As we say, round trip, you are able to come back. You leave and then you come back without having a parallel file. All of the files are centrally located. And this is the focus of our thesis. 2 case studies. 2 case studies are based on direct native file interoperability. In the case study number 1, we have A and B. In A, our focus is how are these model structural data exchange with these three softwares? Do they receive the proper data? And then the next case study is when they receive this data, when they receive this data, are the calculation consistent? Do we have a proper calculation? And then case study number 2, we just try to look at how does the whole structural engineering workflow looks like. How does it look like? And then we will be seeing in these short case studies. So we got this data from Politecnica. They gave us this information in this is one of their projects they did some years ago in Bologna, Italy. And when they provided us this information, they also provided me the structural model prepared by the company. And then I took their structural model. I created my own structural model in Revit, as you see here, the last one. And once I have that, and I then went on to follow the design process using just basic linear static analysis without any seismic analysis or nonlinear analysis or pushover analysis, just something basic to see how the information goes. But then I specifically focus on the Eurocode using this particular reference on the Eurocode. With this reference from the Eurocode, where we consider the load combinations, we created from the analytical model, we consider these loads on the model, their load, live load, wind load, and snow load. And all of these informations, as you see here, were populated in Revit, and we combine, we're using the combination factors. And then later on, we have this, we move to Sophistic, Revit Sophistic, we got this as we came from Dynamo to, we make some of the geometry in Dynamo, and then we populate the data in Revit, and then we went to Sophistic. We were to make sure that the structural models, the material properties, the boundary conditions, the load cases, and load combinations were all transferred properly. These were our interests. And as you know, Sophistic is linked. It has a menu bar directly linked to Revit, and we have it here.
Sorry, Muniru, you are wasting almost. You are reaching the end of the time. So if you can,
okay, I conclude.
To the conclusion.
And then from here, we just follow this cycle, and the result, we got the result for Revit and Sophistic, and then we went to Revit and RFM. The same way we went to Revit and CI Engineer, and then the conclusion was that CI Engineer gave us, Revit and Sophistic gave us 100% data exchange. CI Engineer gave us about, with RFM, we get about, I think 85, 90%, and then CI gave us 88. And the case study number 1 was we just look at the internal forces calculations, and we realized that when you exchange the data with Revit, you get we got exactly the same internal forces. Like Sophistic gave us almost the same, RFM, CI Engineer, there was no big difference. So for this, we were able to understand that, okay, now when you use this process, you're gonna get the same result. And this is one of the interesting outcomes of the thesis. And then the case study number 2 with the workflow like this, and then we got the reinforcement detailing. We designed the slab, and then we got the reinforcement quantities, the same value we obtained from Revit schedule. Sophistic has a way of producing the same result. And we came close to the same quantity of reinforcement needed from Revit and Sophistic. So to conclude, some main BIM uses in structural engineering were identified as interoperability, interdisciplinary coordinations, analysis and design, and documentations. And then interoperability is, we have 3 main levels available, as we earlier mentioned, and the direct link was validated as the most effective way of exchanging load-bearing data, which are structural data, and Sophistic has 100% data transfer, RFM 90%, CI Engineer 88%, and the technical capability of Revit Sophistic workflow was proven, and we also showed that BIM in structural engineering showed tremendous potential, even though there are some challenges. And we recommend that a BIM structural engineer must have the knowledge to perform this workflow. And our study also contributes to international knowledge and the current discourse in BIM and other significant insight for structural engineering companies wishing to integrate BIM into their workflow. So far, this is what we have from our end.